Good day, everyone. In this video, we are going to talk about how to train logistic regression. So, logistic regression is an iterative process wherein we continue updating the weights until some convergence is reached or until some iteration is reached. So, like linear regression, logistic regression also takes the weighted na sum of the predictors or features and weights. So essentially, we have the set of predictors x to x sub j, and then a bias with a value of 1. And each of this has a corresponding weight. So taking the weighted sum, we can represent it into its matrix form, theta transpose x, wherein the theta refers to the weights. So this weighted na sum will be an input to a sigmoid na function that will squish in the values between 0 and 1. Okay, so we can estimate the probabilities. So these probabilities will be the basis of the predicted na labels or classification. So if the predicted na probability is greater than 0.5, then it will be classified as 1, otherwise 0. And of course, we must evaluate the cost or the loss na function. So it's simply um, a way to check the errors. All right. So, and then after computing the cost, we must compute new weights or new theta such that we can minimize the cost, and we will update the weights again with the new computed na weights. So this will be in a loop, will continue until such time that we reach some convergence or iteration. And now the question is, what is the sigmoid na function? So at this point, it is still unknown. And then what is the cost function for logistic regression? And how can we find the optimal weights such that the cost is minimized? And how are the weights updated? So we will answer the questions one by one. So let us start by answering what the sigmoid function is. So the sigmoid na function is in this form, 1 over 1 plus e raised to negative z. So wherein the z is the input to the function sigmoid, and the e is the base of the natural logarithms, or it is also called as the Euler's number, with approximately a value of 2.7, right? So the input is the z. So in this case, the input to our function sigmoid is the weighted na sum, of the weights and the predictors x. So at this point, it is still at a linear na model, right? So using this as an input, the sigmoid function, it will output to, it will wrap this input into this equation, and we will have 1 over 1 plus e raised to negative of the weighted na sum of weights and the predictors x. And this linear na form will become an S-shaped na curve such that the values are squished between 0 and 1. Okay, so now let us replace this equation with 1 over 1 plus e raised to negative of the weighted na sum of the predictors and weights. Now that we have the probability, we can now predict the classification of y, whether it is 1 or 0, depending on its value. Okay. After that, we can now compute for the cost na function after doing the predictions. So the cost function is in logistic regression is called as the log loss or the binary cross entropy loss. So it is binary because it has two cost functions for each na categories or for each na labels. So if the true labels is equal to 1, then we want that the cost function is negative log of the estimated probability P. But if the true label is 0, then the cost function is negative log of 1 minus P hat. And it makes sense because the sum of these probabilities P and 1 minus P will be equal to 1. Okay, so if P is the probability that Y is equal to 1, then it makes sense that if it is not 1, then it is 1 minus P. Okay, note that the probabilities will sum up into 1. So we want that if Y is equal to 1, we want high na probabilities. Okay, so the objective function is to train such that the probabilities will be high for the positive na instances. Okay, but if the true na classification or true label is equal to 0, so we want that the probabilities are low. So let us explain that further. So if the true classification is 1, then we want that the probabilities are also close to 1, because as you can see, the cost is increasing to infinity when the probability is getting far away from the actual 1. So meanwhile, we want that the probability is low or very close to 0 if the true classification is 0. Why? Because the cost, as you can see, is increasing as the probability is getting away from 0. So now, this cost na function may be represented in only one equation. So we have cost of theta is equal to negative y times the log of p minus 1 minus y times the log of negative 1 minus p. So the y's here are the true na y na values. Okay, and then if true y values that has a value of either 0 or 1, and the p is the probability that y is equal to 1, and probability that y is equal to 0. So how is this equivalent to this representation? So suppose y is equal to 1, then if we plug that into this equation, the one that was presented earlier, then it will cancel out the second term, because 1 minus y, which is equal to 1, will be 0. So this will be canceled out, and we'll be left with the first term, which is negative log of p. While if y is equal to 0, or the true classification is 0, then the first term will be canceled out. Okay, and we will be left with the second term, and it will evaluate to negative log of 1 minus p. So we want a log loss score that is smaller. Okay, so because that means that there is a bigger na gap between the classes. So as you can see, this class 0 are also squished into 0 or probability 0 or close to 0, while the true class 1 is also closer to 1. Unlike this higher na log loss score, wherein the, let's say, the probabilities of those true class 0 are also close to 0.5 or close to 1. Okay, and same for those positive instances. So the cost function is simply the average na cost for all na samples. So this equation, or the cost, is simply the cost for a single na instance. And in order for us to compute for the average cost for all na samples, then we must compute for the cost for each na instance, sum them up, and divide by the number of samples to take the average. Okay, and replacing this cost with this equivalent equation, then we have negative 1 over m, and the sum of all the cost y times log of p plus 1 minus y plus times log of 1 minus p. And note that here we have added a subscript of I, which means that we are computing for each na instance or each na sample. Okay. So we wanted that this cost will be minimized. So, and we can do that by finding the best na weight or best na theta. So note that the P or the estimated na probability P may be computed from the sigmoid of the weighted na sum negative theta transpose and x. Okay, so we wanted to fit the parameter theta such that we can minimize this cost na function. So now that we are done with finding out the performance of finding out the cost function for logistic regression. So let us move on to updating the weights as well as computing the new weights. So the question is how we can find the optimal weights such that this computed na cost will be minimized. And using the computed new weights, how can we update the old na weights? Unfortunately, there is no closed na form for computing the optimal weights in logistic regression, but we can use gradient descent instead. So as you can see here, we have mentioned earlier that those that have positive na instance, we wanted to have high na probabilities, and those that have negative na instance will have a low na probabilities that are also close to 0. Okay, so and these probabilities are represented by the red line. By gradient descent, so we want to take that, we want to find that best na weight or best na theta such that the sigmoid na curve are also getting close to the optimal. So it is worth mentioning that in logistic regression, our goal is not to minimize the square root na distances, but rather to get the probabilities as close to the true na probabilities. So in the lower half na animation, we can see how the cost na is dropping simultaneously after each na epoch or iteration, then finally end up in a global na minimum of the surface plot. So again, if y is equal to 1, then we want that the probabilities are close to 1. But if y is equal to 0, we want that the probabilities are also close to 0. So, and we can do that by finding the partial derivative of the cost function with respect to change in theta sub j. So this cost function, we want this to be minimized. And to do that, we can compute for the partial derivative. So the partial derivative will tell us which direction we are going to go to find the global minimum. And it will also tell us how much change in the weight is going to take place. So this numerator is the change in this cost function with respect to the change in theta. So in other words, we are going to change the weight a little bit. And with that change in the weight, how much is the change? How much is the change in the cost? Okay, so this is this is how it evaluates to. Okay, so the partial derivative of this cost function is equivalent to the difference of the estimated na probabilities minus the and the true na classification, which is either 0 or 1, multiplied to the value at the j feature, and summing this all up and taking the average. Okay, so plugging that into our equation, we have the theta sub j equals the old na theta sub j minus the learning rate times this derivative. So the learning rate will tell us how big of a step we are going to take. So if the learning rate is very large, then this value will also be so much bigger. But if the learning rate is small, then the step will also be so much smaller and will make the process or will make the conversion slower as well. So it's up to you to experiment what learning rate to use. So now we know that this P is the estimated na probability, which is equivalent to the sigmoid of the weighted na sum of the weights in the predictors. So plugging that in, and then we arrive into this equation. And lastly, this sigmoid is equivalent to 1 over 1 plus e raised to the negative na weighted na sum. And so plugging that into this equation, we arrive to this final na formula for computing the new weights as well as updating the new weights. So this is now the gradient na descent. So after all the derivations, so we will simply repeat this process, simultaneously updating all the weights until such time that we reach some convergence or number of iterations. So you are already familiar with this one, but let us have a brief review. So this is the part where we update the weights. So this is the old weight set with the new value of theta. And this is the learning rate, which will tell us how much big of a step the gradient descent is going to take. M is the number of samples. And this is the P, or the probability of Y to be in a certain class. So this is the predicted na class of Y. And this is the true class or label, which Y is the true class or label that has either a value of 0 or 1. And then the X is the value at the J feature. So for each instance, it computes for the prediction error. So that this is denoted by the difference of the predicted class and the true class. And it multiplies that by the J feature and then computes the average over all training instances. So now we are done with updating the weights and computing the new weights. So these are the references, and you can check this out for further readings.